Hello, NASA Seas. This is Exotransits, an analysis of exoplanets using HOPS and Batman by the Seas Exoplanet Transit Exotransit team.
So first, let's start with what is an exoplanet. So exoplanets are planets outside of our solar system, and as of now, over 5,900 have been confirmed, with up to 15,000 more still awaiting confirmation. The first exoplanets discovered in 1992 were orbiting a pulsar called PSR B1257 plus 12, which you can see in the top right. These were rocky planets and marked the beginning of exoplanet research. In 1995, 51 Pegasi b became the first planet found orbiting a sun-like star, shown in the middle. Then we also have HD 209458b, shown at the bottom, which was the first planet where we detected an atmosphere, and also the first discovered using the transit method, which we use at SEAS. Each of these discoveries was a major step forward in exploring planets beyond our solar system.
So, why are exoplanets so important? Exoplanets are important because they help us understand how planets form and evolve, whether life might exist beyond Earth, and how diverse planetary systems can be throughout the universe. By studying exoplanets, scientists can test theories about how planets form and evolve, and compare different planetary systems to our own. The ongoing search for exoplanets has driven the development of powerful telescopes and advanced detection methods, pushing the boundaries of our ability to observe and study faint, faraway objects in space.
Building off of the importance of discovering exoplanets, let's look at what makes an exoplanet potentially habitable. To determine this, scientists look for three key conditions. First, the planet must be at the right temperature. This means its orbit must be within the habitable zone, also called the Goldilocks zone, where it's not too hot or cold for liquid water to exist. The distance for this zone varies with the temperature of the star, as shown in the diagram. Second is a stable orbit. If a planet orbits too erratically, its climate would constantly change, making it hard for life to thrive. A steady circular orbit helps maintain climate stability over time. And third is an atmosphere. It helps regulate temperature and provides gases like oxygen, which life as we know it depends on. One of the most successful ways to detect exoplanets is through the transit method. This technique looks for tiny dips in a star's brightness when a planet passes or transits in front of the star from our perspective. This method is extremely successful. Out of over 5,333 confirmed exoplanets, 4,395 have been discovered this way as of July 17th. Major telescopes like TESS, Kepler, and the James Webb Telescope are used to observe these dips and collect data. These dips are graphed as light curves, which show changes in brightness over time. By analyzing these graphs, we can detect when a planet passes in front of its star. But there are a couple caveats. The planet needs an almost edge-on orbit to be detected with transits. Also, there's a higher chance of false positives, like when an asteroid or debris passes in front of a star and creates a dip that looks like an exoplanet transit. Here we can see a labeled light curve. On the y-axis, we have the relative flux, or brightness, and the x-axis shows phase, which represents time. When the planet starts passing in front of the star, we can see a dip called ingress. The light remains dim during the transit duration, and then rises again during egress when the planet exits the star's view. The drop is about 3%, from 1.0 to 0.97, meaning the star's brightness decreases slightly but measurably. These graphs can also help us determine the orbital period of a planet by measuring the time between transits.
Now, moving on to our exoplanet candidates. Our first exoplanet candidate was WASP 135b. It is a hot Jupiter gas giant originally found through the Wide Angle Search for Planets, or WASP, detection program. WASP 135's transit helps test orbital alignment and probe star-planet interactions. Looking at the graph on the right, we were able to produce a clear graph of the exoplanet's transit as observed by the notable dip in the star's flux as the exoplanet passes between our telescope and the star. Looking at the observed minus calculated, or O minus C value, we see a small positive value. This means the transit occurred slightly later than predicted. However, minute differences like this are to be expected as neither HOPS' predictive algorithm nor assessment is 100% accurate. Our second exoplanet candidate was WASP 41b. As its name suggests, it was also found via the WASP detection program. Its transit in particular was also helpful in testing orbital alignment, but also transit timing variations and star spots. While WASP 135's transit was detected later than expected, WASP 41's negative O-C value indicates the software detected a transit that occurred slightly earlier than predicted. This was still an acceptable difference. Our final WASP-detected exoplanet is WASP 19b. Of all the exoplanets we analyzed, WASP 19 had the shortest orbital period, taking only 4/5 of an Earth-day orbited star. When discovered, its transit was useful for atmospheric spectroscopy. Our next exoplanet is Corot 1b. This gas giant was discovered using the French Convection Rotation and Planetary Transits telescope. It was the first exoplanet discovered by the Corot telescope, which was a pioneer in exoplanet photometry.
Okay, and next we have Kepler 41b. This exoplanet was discovered by, as the name suggests, the Kepler Space Telescope. It is a hot Jupiter with a low density and is important because it shows phase curve modulation, or that is, albedo and secondary eclipse constraints. One thing to note is that this exoplanet orbits a G-type star, which means that the host star has a very similar temperature and characteristics to our Sun. As you'll see, a G-type star is the most common classification among these initial 8 confirmed exoplanets. Then, we looked at Kelt 23AB, which was discovered by the Kilodegree Extremely Little Telescope. This exoplanet has quite similar characteristics to the previous one. However, it's special because it has a bright host star, which makes it accessible for community follow-up and atmospheric work. Next, we have HATS 18b, another gas giant discovered by the Hungarian-made Automated Telescope Network South. This planet has extremely strong tides, a high planet mass, and a short orbit, making it great for studying orbital decay. And finally, we have TRES 5b, which was discovered by the Transatlantic Exoplanet Survey, which is a network of 3 ground-based telescopes. This exoplanet is located inside the Cygnus constellation and has very similar properties to the last 3 exoplanets. However, it does orbit a K-type star, which is much cooler. As you can see, this exoplanet has very deep transits, which makes it a benchmark for studying hot Jupiters around faint stars.
TESS is the Transiting Exoplanet Survey Satellite, launched in 2018. It is managed by MIT, Harvard, and Smithsonian, and by 2020 it had searched about 75% of the sky. It has found 600 confirmed exoplanets. TESS objects of interest, or TOIs, are significant findings from TESS that require further investigation. We considered 3 confirmed exoplanet TOIs. Because the TESS project was so exhaustive, some TOIs could be more elusive or obscure than other exoplanets. Because of these difficulties, we turned to our alternative method of analysis, resulting in different-looking light curves. Our methodology will be detailed in the next section. TOI 519b is a gas giant orbiting a red dwarf star. It is about the size of Jupiter, and it is roughly 60 times closer to its sun than Earth. This exoplanet's equilibrium temperature is around 450 degrees Celsius. Water cannot exist as a liquid here, meaning that TOI 519b is not capable of supporting life. An exoplanet this massive is relatively rare around a star as small as a red dwarf. TOI 674b is classified as Neptune-like, and it is about half the size of Jupiter. The exoplanet's equilibrium temperature is around 350 degrees Celsius, much too high to support life, once again likely because of its proximity to its star. This exoplanet is fairly unique, as not many Neptune-like bodies have such short orbital periods. TOI 540b is an interesting case because, as you can see, the light curve that was produced from its data is extremely weak. In fact, it is not larger than the error bars of the data. The fact that we were not able to reproduce the transit of TOI 540b will be discussed in the results section of this presentation.
This slide demonstrates our data used, and the data used was from the SARA data from SARA to Lolo. Now, typically astronomy data files are stored in a .fits file, and they contain data ranging from the spectra of stars to the light curves of exoplanets in this case. And this data was taken by the Southeastern Association for Research in Astronomy at SARA to Lolo. SARA at SARA to Lolo is a 0.6 meter telescope located at Sikyo, and the main goal of SARA is to allow a broader swath of the scientific community access to astronomy data and these telescopes. And our data from SARA is a series of full-frame images of the night sky taken by the SARA telescope, and it contains both target stars and additional comparator stars, and this is the data that was utilized by HOPS.
So what is HOPS? HOPS is a software tool made for analyzing how a star's brightness changes, especially during exoplanet transits. It uses aperture photometry to measure brightness and compares your target star to 2 to 4 stable stars nearby to account for background light. HOPS also uses an algorithm called MCMC, also known as Markov Chain Monte Carlo, to fit the data and model the planet's transits, helping us figure out its characteristics like size or orbital period. Now that we know what HOPS is and what it does, let me walk you through the actual procedure. First, make sure all the raw images and calibration files are saved and organized in one folder. Consistency is very important because the camera settings have to match across all files, and file names needed to follow a pattern so HOPS could recognize them easily. Also, make sure to include enough calibration frames and avoid any light leaks or contamination when capturing them. Next, open HOPS and load your data folder. HOPS will then check all the file details, things like exposure time and filter, using the FITS header. From there, it automatically generates master calibration frames and corrects your science images. Once the images are calibrated, you have to check their quality. HOPS gives you tools like sky and PSF graphs to help spot any bad frames, like ones affected by clouds or tracking issues. Then HOPS aligns the stars across all frames so that the target and comparison stars are in the same position in every image. It usually does this automatically, but if something looks off, you can just step in and adjust it manually. This part is where you actually select the target star you were studying and a few stable comparison stars nearby. Make sure they are about the same brightness and color to give reliable results. Then adjust the aperture to make sure it includes the whole star but avoids nearby objects. After running photometry, check the light curves to make sure everything looks consistent. Finally, once you have your light curve, move it to fit the transit. HOPS gives you a couple of options like aperture or PSF fitting. Enter the planet's parameters and run the MCMC fitting. The goal here is to fine-tune the model and check how well it matches the actual data by looking at the residuals.
This is our results from HOPS. Of the 11 exoplanetary candidates, 8 of these planets were able to be analyzed by HOPS. Specifically, the TOI candidates, however, were the ones that were failed to be analyzed by HOPS. All of these exoplanets have planetary parameters extracted that are fairly close to the literature. However, HOPS does have some deviations, especially in terms of the inclination parameter. HOPS typically utilizes the quadratic and linear D-trends in order to evaluate the fit. And as you can see, these are the fits for both TRIS 5b and KILT 23ab. Our alternative methodology is Batman, also known as the Basic Transit Model Calculation. Batman is a light curve fitting software algorithm introduced by Laura Kreidberg in 2015, and it is a toolkit for modeling exoplanet transit light curves, which accommodates various stellar limb darkening laws, while also being less computationally expensive. When Batman is combined with a Markov chain Monte Carlo fitting algorithm, Batman effectively does HOPS' job. However, it uses a different light curve fitting algorithm and is more code intensive. The data used by Batman, unlike HOPS, uses the light curves rather than the full-frame images themselves in order to fit for the transit parameters. Therefore, we need to take data from a different source, and this data was taken from the Mikulski Archive for Space Telescopes, MAST Archive, specifically from the Transiting Exoplanet Survey Satellite. However, the data is still a light curve fits file. As you can see, this is the MAST Archive snapshot, and we have a raw light curve file for TOI 674. This is our step-by-step data analysis unit using Batman. So our first step was to utilize the data initialization factors by initializing all of the FITS files into the Jupyter Notebook environment. Then, in order to ensure that Batman would run properly, we ran a single test with Batman in the Jupyter Notebook environment. Then we coupled the Batman light curve model and a Markov chain Monte Carlo fitting algorithm in order to ensure that we got proper fits, and we ran the Markov chain Monte Carlo fitting algorithm for 5,000 iterations, the same amount of time that the HOPS iterations ran for. Then finally, we extracted those exoplanetary parameters from the Markov chain Monte Carlo. This describes our results from Batman. Of the 11 exoplanetary candidates, 10 of the candidates had fits that our team was confident in based on the diagnostic corner and trace plots provided by the MCMC. However, one fit for TOI 540 had a signal-to-noise ratio that was far too small in order to ensure a confident fit. And these exoplanet fits have semi-major axes, radii, inclinations, and center times of transits, essentially T0s, that are within the error bars listed on the NASA Exoplanet Archive. So as you can see, there is a Batman fit of Kelt 23AB as well as a Batman fit of Kepler 41. I would like to highlight a few case studies from the Batman fitting algorithm. The first case study is to ensure that both Batman and HOPS are working properly, and this case study utilizes WASP-135. According to the NASA Exoplanet Archive, WASP-135b has a radius of approximately 1.3 Jupiter radii, and when we convert that to stellar radii, it gives us a value of 0.1428, and as you can see, the radius given by the Batman Markov chain Monte Carlo fit is fairly consistent with the NASA Archive itself. Our second case study is an exoplanet candidate that caused issues with the HOPS fitting algorithm. However, it is able to be fit utilizing Batman. According to the NASA Exoplanet Archive, TOI 674 has a radius of approximately 0.073. Then when it is converted, we get a value of 0.111. And as you can see with the extracted exoplanetary parameters, the radius value is consistent with the values that we have extracted. In addition, the overall fit seems to be fairly consistent. For TOI 519, we want to showcase the steps that were taken throughout this entire process. So we can see for the outputs, we do have an overall fit that is very good. In addition, the diagnostics for the fit, the trace plots and corner plots, are very good and very consistent with what we were expecting. In addition, the extracted parameters are also incredibly consistent with the values found on the NASA Exoplanet Archive. For a final case study, we would like to discuss TOI 540, as TOI 540 is the only exoplanetary candidate that couldn't confidently be analyzed by either Batman or HOPS. And the reason for this is most likely due to the low signal-to-noise ratio of the data itself, as the transit signal appears either weak or non-existent. However, further research is needed to examine and understand if TOI 540 is indeed an exoplanet, and this is most likely one of our more interesting findings during this entire internship process.
A key challenge we faced was occasional technical issues, but by working together and troubleshooting as a team, we were able to solve problems efficiently. We explored real-world astronomy workflows and gained hands-on experience with exoplanet transit analysis. Our team used specialized tools like HOPS and Batman to process astronomical data and generate life curves. Through SEAS, we built not only scientific skills, but also learned valuable collaboration and coding techniques, especially in Python and data visualization.
Hello, my name is Juhi, and NASA SEAS has been a truly transformative opportunity, and it has given me the opportunity to collaborate with mentors and peers to gain incredible hands-on experience, especially with Batman and HOPS.
SEAS gave me meaningful insight into the welcoming work culture of NASA. It also honed my technical and soft skills that are necessary for a future career in aerospace.
My name is Jameson Palmer, and I believe that SEAS has given me invaluable hands-on experience with the physical sciences in a way that schooling never could.
Hi, I'm Juhi Bhatt, and NASA SEAS has given me insight and direction into what a career in astrophysics could look like while also connecting me with a group of like-minded peers. I'm very grateful to have developed my research skills and furthered my love for space.
Hi, I'm William, and the SEAS program has been an incredibly exciting and rewarding experience. It gave me the opportunity to dive deep into the field of exoplanets and astrophysics, allowing me to explore topics I've always been curious about in a hands-on and meaningful way.
My name is Mina Uzgoren, and the NASA SEAS program gave me valuable hands-on experience in exoplanet transit analysis. I developed skills in Python, data visualization, and scientific collaboration. This opportunity made me excited about pursuing space research in the future.
Hi, my name is Samuel Thomas. SEAS has given me an incredible opportunity to collaborate with peers, learn from mentors, and work with advanced analytical tools. I'm so grateful for this experience, which has further inspired my future goals in STEM.